Hello, yeah, so thank you for the introduction. So I wanted to talk a little bit about how we have been using different AI machine learning techniques in monitoring public information in the context of COVID. So what is the general problem is we would like to detect early warning signals related to COVID vaccinations and side effects. And we have been working with this with LinkAlong, which is a startup from my lab that has been developing a platform that is called Peak that has been built to perform this kind of tasks. So generally speaking, there's obvious interest in COVID. There is a large interest also in the deployment of vaccinations and what are the potential side effects. And so there is, of course, a lot of the official scientific work that is being done in that. But in kind of in a complementary approach to that, it is also useful to monitor what kind of information is revealed on public sources. So that could be of interest also for the specialists in the domain that are working on these type of questions. So what exactly could you think of monitoring in this context? So you can, of course, detect announcement and news, both from media, from official sources, and so on. And keeping up to date is, of course, an obvious thing to do. But in the public space, you find also other information, people reporting on their personal experiences. And one potential for that is to detect, for example, early warning signals on new types of side effects that are probably unknown, but also to get some more statistical insights of what type of side effects occur in specific contexts. While doing so, what you want to do is, of course, on the one hand, eliminate also misinformation, which is critical if you want to get some serious data, and also in some cases consider popularity. And these are the kind of tasks that are supported by the technology that we have developed. So if you look more closely, what is it one day in the COVID vaccine side effects in the public space? Roughly speaking, if you try to capture all relevant data, you will find a typical amount like 30,000 posts on a platform like Twitter, a couple of thousand documents also on the web. But in this mass, there's of course a lot of noise, and there is nevertheless some very relevant content contained. So, and with the methods I will be talking a little bit later, you can find a couple of dozen of real testimonials of where people report on specific experience, reports, for example, on fatal cases that have been occurred. And in that you find then also some content that comes from anti-vax accounts. Now, when trying to kind of capture this nevertheless quite sparse information, this huge mass, you are in the typical information retrieval dilemma. On the one hand, you want to increase the recall. That means you want to get as many possible documents that are potentially relevant. This implies that you increase also potentially the noise that you have in the data. So then you want to have, on the other hand, high precision in order to avoid wasting time of analysts producing credible data. But then the more you increase precision, you are kind of risking to miss relevant information. And so using basically the techniques I'm going to describe, we try to optimize this trade-off. So let's talk first about recall. That is kind of the more traditional problem tackled. So typically you want, first of all, to capture all relevant information. And now if you look what is happening, for example, on the internet where people are not very precise with language, if you would like to capture, for let's say as an example, the Pfizer vaccine, I can show you here a couple of examples of how people are really mentioning it. And so you have to basically figure out what are all these different ways of talking about the same topic. And the traditional approach would be to guess them. And that's, of course, not something that really works in practice. So there we are using some AI that is building so-called word model that essentially tries to understand the meanings of words and help basically to retrieve these types of different kinds of mentions of the same topic. Doing that, we are relying on so-called word embedding models. So word embedding models, they learn about the similarity of words, and they map basically the words in a space, as you see in this graphics. And if you can read it, you see that, for example, the model could learn the difference between different vaccines, and this purely by reading all the text, analyzing the text without any instruction from the outside. And you can consider these models also as a sort of shallow neural network model. And we have packaged all of this in a way that basically an expert can curate a taxonomy using these models that allows to capture all relevant content in an efficient way. But now, and then you can use that to either search or to classify the data correspondingly. But now this is not enough. So there are cases where word-based models simply do not work well. So here is one example. We would like to identify reports on fatal cases. So you would typically use words like death or something similar and vaccine, and we would like to capture information. But if you look at the examples, you see you can find positive and negative examples, true reports on such cases, and other types of posts that use the same terminology, the same words, but they're not at all talking about reports. And how can you distinguish those? And a purely word-based model, as I have just shown before, simply does not work in this type of situation. So, and this is where we basically started to employ deep neural networks, so-called transformer models. So these are language models that do not understand simply this meaning of words, but they understand the meanings of whole sentences. So they could distinguish the sheriff received his first shot from I shot the sheriff, which if you look just at the words, you cannot. And we have been using that for this specific case of identifying fatal cases. And the result has been that if you take a purely word-based approach, you would get a couple of hundred posts per day that an analyst would have to inspect to figure out the interesting cases. But with using our approach, we could reduce basically the volume by a factor of 10, roughly speaking. And just a quick word on these transformer models. Where do they come from? Originally, they come from language translation. They have been developed by Google and others. They're deep neural networks that essentially learn about relationships among different words in the same sentence. And they are very huge models. They have hundreds of millions of parameters. They're trained on huge data sets. They're correspondingly also expensive. And they're used nowadays in different contexts. So just to give an example, Google has employed them now since October also in the context of Google search. So just to show you a typical outcome. So in one of the use cases, analysts were interested to learn about fatal cases in contexts where little official data is available. So if you look, for example, at Sinovac, which is not one of the standard vaccines used in Western countries, so they're purely documented. In addition, in countries where data is also not easily accessible, in that case, it is Thailand. So they could reconstruct basically the timeline of all known cases of fatal cases following up the vaccination, and so gain insights that, in fact, they were not fully recoverable from the official sources that are available. Also, another use case that we have been studying, were so-called testimonials, where people are self-reporting basically the side effects following vaccination. Again, if you would use a purely word-based approach, you could not even distinguish a real report from a simple question, does this vaccine produce this side effect? So basically, if you would not have such a mechanism in place, you would essentially monitoring a large part of noise. And so we use this to really identify this type of specific reports, and the system can relatively reliable, of course it's never 100%, extract such reports, and this can be further used for different purposes. So for example, for producing some statistical information, but even more interestingly, it is also being used to identify potentially new side effects, rare side effects, and to basically give indications to the analyst of what potential problems could have been occurring. Now, just to be very clear, this does not provide any proof that these side effects occur. This does not replace medical studies, but the idea is that it is really leading experts on the track in order to basically then verify whether some real phenomena is behind, or whether it was just some random message that has been produced by someone. Okay, so yeah, I'm running a bit fast, but no worries. So we have more time for questions. But so essentially, what we have been doing is that we have been implementing such an event-based surveillance system that kind of does complement standard safety surveillance that is in place. We have been using machine learning and AI to do text classification. And in particular, using deep neural networks, we could really overcome some of the very strong limitations of traditional methods in text analysis in terms of really classifying documents based on a very subtle differences in sense that you cannot do on a purely keyboard-based approach. And we have also produced essentially evidence that analysts can in fact produce more meaningful information. They can save time, and they are finally happy with the results. And if you want to get in touch with me and get more details about the background of the project, please just write either to this email or visit also our website. So thank you for your attention.
Thank you, Karl, for your interesting talk. So the first question is, can you provide us a bit more detail about the training of the transformer network? So on which kind of data and how large the corpus for understanding which messages are for actual cases and which were not, and if it was a human annotated data set that you did your own, or how did you get those data to train the model?
So actually, we have been using pre-trained models, and using approaches that are based on few-shot and zero-shot learning. So we need not really massively now annotated data sets, but we can leverage basically pre-trained models and kind of tune them with very few examples. And it turns out that this kind of works well. It's not trivial to get it right, but you can avoid at least major efforts in labeling.
Okay, thank you. And the second part, so once that you discovered that a message was related to a case, is there a way, an automatic way to understand if multiple messages were referring to the same case, or is that the part that the analyst has to carry out?
Yeah, that's a very good question. We have been putting in place mechanisms in order to basically filter out, so to say, already detected events. This is a very important question, actually. So basically, you continuously improve, in a sense, the selection of messages that you still consider, because, of course, there is a lot of repetition. And many cases will be kind of reported and re-reported over time. And efficiently filtering those out is another measure that we put in place in order to reduce the data volumes.
Okay, so the very last question is, if you are considering to apply your approach, your pipeline, also to other social media, like for instance Reddit, and also for surveilling the effect of other drugs that maybe have not such an attention as COVID vaccine.
Yeah, so what concerns other platforms, there is no fundamental reason that we would not use them. And we are, in fact, using data from other platforms as well. I've just given Twitter as one example, because this is, of course, as everyone knows, the most easy to access type of data, but we're working also with other sources. So that is a kind of an orthogonal problem. And what concerns the use of the mechanism to other types of pharmaceutical problems, so basically problems related to pharmacovigilance, we have been doing testing, so it works in very similar ways. Of course, in general, the key question is, as usual, first of all, is there interesting data out there? So it depends, of course, on the popularity of the drugs, of basically how much content you find that is worthwhile to analyze. And so, but we see that for at least for more popular drugs, you can more or less do the same thing. So you can monitor side effects, but you could also monitor other aspects following the use of such drugs.